So welcome back, everyone. So the next lecture today is by Professor Kasturi Saha from IIT Bombay. She's going to talk to us about diamonds and are forever and for everyone. Okay. Yes.
Thank you. Thank you, Anil. We had a fantastic morning session so far. So we were hearing about extremely precise clocks and, very sophisticated system that has been developed over, several decades. Now I'm going to tell you about diamonds, and you already heard Professor Arup talk about, diamond-based quantum sensors, nanoscale sensors. As you've already probably gotten a feel, in comparison to the clock system, this is a much more dirty system. Okay, it's a rugged system, it's a dirty system, and really not much of sophistication in it. But it's still a quantum sensor. And today, I therefore want to talk about diamonds that are forever and without gender discrimination. It is for everyone. Okay, so let's get into what the outline of my talk is going to be. So I will just touch upon color defects in diamond just to revise what you already heard in 2 lectures a little bit in detail maybe, and then talk about quantum sensing protocols, again a little bit of refresher, and then 2 specific cases I want to talk about. One is rotation sensing, a piece of work that I started during my postdoctoral work, and this is in fact rotation sensing was when I was introduced to NV centers, and then finally I'll talk about dynamic wide field imaging, what we are doing at IIT Bombay as an application of the to show you the power of this kind of a quantum sensor. Okay, so here are some pictures that you will see throughout the talk. This is the NV diamond, and this is the ODMR, and this is really the diamond that glows orange as you shine, as you excite it, and it's visible by eye. Okay, just to brush up again, as you have already heard, diamonds are very defective. In fact, the colorful diamonds are the most defective ones. What you see in a gemstone store, you probably would have seen these brightly colored diamonds, and they sell at very high price. And what they don't tell you, or what most of the time they don't know, is that these are the defective ones. And it's yellow because, as in nature, when yellow diamonds were found, they were essentially because when diamond was, developing in the Earth's crust, there's a lot of nitrogen content in the air, right? So nitrogen seeps in to that diamond carbon lattice, and so that gives it this bright yellow color because it emits in this yellow region. Okay? And then if you have boron, you get this nice bright blue color. But of course, when you work in the lab, things don't look bright and shiny like this. It looks mostly like this, almost like colored piece of diamond. So I tell my students here, and Prajita is here, so that don't lose any of them. Because if they fall on the ground, you don't know. You will not be able to make out by eye. And it's very difficult because most of the diamonds actually don't look bright and colored like this. They actually look like this. In fact, they look like this. And it's literally just a small piece of, looks like a piece of glass. Okay, and even like it's about 2 to 3 millimeters typically in length and breadth, and then you have a thickness of about 500 micron, or it could be even thinner. We have about 40 to 50 micron thin sheets of diamond as well, or membranes of diamond as well. If you crush them, they look like this. These are nano diamonds, and you heard applications of some nano diamonds before. If you fabricate on them, like for instance, you make some pillars, or you make different kind of photonic crystal structures, etc. You can also make the scanning tip, like the standard AFM microscope. You can attach this special tip with a diamond tip in it, and you can have an NV center in it, and that is very useful for scanning magnetometry. So these are all the different varieties of samples that you can see in the lab. These particles can range all the way from 30 nanometer to almost 120 nanometer size or so, and there can be various different applications of them. a very important varieties are these single crystalline. In fact, these are single crystalline plates, and you can implant on them, or you can, when you are growing, you can also have a layer of NVs in them, and they are also important for different applications. And this is one of the biggest challenges in our field, is really how you make the best quality CVD diamonds or HPHD diamonds with the best quality NV centers in them. So this has been developing over several decades now. There are gemstone makers who make CVD diamonds as well. Now lab grown diamonds are very popular, but lab grown diamonds with the right kind of properties are the most important aspects that one has to really develop. And Element 6 is the company which is essentially an arm of De Beers, is really the pioneer when it comes to making and fabricating these kind of diamonds that are relevant for doing quantum sensing. And they have been working on it for, in partnership with several universities over, several, like 20 years or so. And finally, now they are commercially selling them through Thor Labs and through other vendors, etc. And they also have their own. Now, there's another variety which is essentially the pink diamond. And pink diamond is when you have, in the diamond, you have the nitrogen, which is a substitution, which is essentially if you have only nitrogen will give you yellow. But along with it, if you have vacancy in any of the 4 other arms of the tetrahedron, you basically form a nitrogen vacancy complex, and along with it, it also captures another electron from the surrounding, forms what is known as the NV minus complex, right? So this is the NV minus that is of interest to us. There are other charge states as well, NV0 and NV plus, but the most important one that has the stable electronic structure is actually what is interesting for, what is interesting for us. Okay, just to for Saikat, because he mentioned what we are interested in, I want to show you some of those images. But first, this is again the diamond lattice. You have the nitrogen and the vacancy along with an electron. This is in fact a real artificial atom. Okay, so unlike, so I think Subhadeep is not here, but this is actually repeatable. So it's not like quantum dots where the frequencies change. This is actually a fixed frequency. Okay, so every nitrogen vacancy center has a 0 phonon line at 637 nanometers. And so this is truly an artificial atom. Of course, unlike free atoms that you've been hearing about, here because this is a solid state matrix, there could be other atoms around it, and that perturbs the system. And you've already heard about carbon 13, you've heard about other nitrogen defects which could be sitting around just next to the the NV minus, and those are all perturbations to your NV minus. So referring back here, so this is the electronic structure. You have a ground state triplet. Then, so it's the degenerated plus minus 1 separated by the 0 phonon line, which is or 0 field splitting. This is 2.87 gigahertz. And when you shine green light, essentially you excite the NV system, and then it decays back with 637 as the 0 phonon line. And then you have a phonon band, which goes all the way up to, say, 750 nanometers or so. Degeneracy can be broken very easily with a bias magnetic field, and I'll talk more about the magnetic field and issues with the magnetic field. This lecture, essentially, I will try to highlight some of the important challenges of setting up such an experiment and focus on the really basics of some of the things. So you can see, you can shine with a green laser, you collect out the fluorescence. If you build what is known as a confocal microscope, right? A confocal microscope, unlike a standard microscope, which cannot discriminate between Z planes, a confocal microscope can actually discriminate each and every Z plane, right? With, of course, there is a, there's a limit to how well it can discriminate. Typically about a micron or so, or 2 times your diffraction limit. So, but the spots you can resolve, here you can see that this is actually, unfortunately, this is not visible, but this is about within 500 nanometers or so. So within the diffraction limited spot, you can see very nicely, these are all the emitters that are there. This was a very recent scan that we did. This is in the Z plane. You can see the emitters, in the Z, and this is your XY plane. And so you can see very nicely, you can sit on one emitter and work with one emitter or so. Now, of course, as Saikat already mentioned, we really don't know whether they are 1 emitters or 2 emitters or 3 emitters or so. But as an experimentalist, we know there are standard techniques, for instance, like a G2 measurement, because every time you excite, with a green laser, it always emits the 0 photon at 637, and that's a single photon. So you can repeatably, so it's a deterministic single photon source if you work with a real single emitter. But it's a challenge if you work just with a confocal microscope. So you saw that Professor Arup already showed you like a STED image where they could really look into in a very super resolved image where they can focus into images. But then you can also perform experiments of G2 or correlation measurements on the single photon to ascertain whether they are single photon emitters or not. Now, when you apply a bias magnetic field to one such emitter, you can see that you can have, instead of a 3-level system, you have a very nice workable 2-level system. So you can drive the transition between 0 - 1 or 0 + 1 and work with it as a 2-level system. So on the Bloch sphere, essentially you're going to work with 0 or -1 or 0 + 1 as your simple 2-level system, right? So this is the basic architecture of our system. And now you can work in 2 extremes. The first image I showed you of the diamond that was glowing orange is by naked eye. You can actually see it by naked eye, all that bright orange. And that's because if you have many, many emitters, okay? And that's the other extreme region when you have a very dense number of emitters. But you can also have samples like this where you can resolve each of the emitters, right? So just to tell you how and recap on how we do optical control of the system, let's say this is my electronic structure. What I start doing is I start pumping with my green laser, and you see that you can have a thermal distribution of the NVs if you, let's say, take a cluster of NVs. Now let's keep pumping and let's see what happens. So every once in a while, when one of the NVs start from a plus or a -1 state, we'll always go into this spin non-preserving state or a non-radiative state, and actually comes back down to the 0. So 0 to 0 is always spin preserving, but the others are not. And so what happens is if you keep pumping the green light, essentially what you get is polarization very nicely into the 0 state. And this is a very advantageous system because this is a room temperature system. So, and you have with almost very, very high fidelity, you can get up to, a very nice state preparation into the 0 state. Right, so we can initialize the system. Any quantum system first needs to be initialized because that is the first starting point. So let's start here and let's see what happens to our fluorescence. Okay, so can we really do readout of the state from this? Yes, we can. As you can see, if you keep pumping from 0, after you initialize, you will see something like this over time. But suppose it starts from this, plus or -1 levels, it goes to this, metastable state that you have. And this actually causes a slight differential in the contrast, or rather in the fluorescence, because of this decay pathway that exists. And so what you see is that you have a spin dependent fluorescence. And this is really the essence of our NV centers, because now you have a mechanism that if you actually have a laser that can be, have a pulse width of say this 200 or 300 nanoseconds, you can distinguish between the 0 and the -1 and +1 levels. And this is really the heart of our system, where you have spin dependent fluorescence, or what we can then use to perform optically detected magnetic resonance. Okay, let's see how it works. So for a typical experiment, you would apply a bias magnetic field, try to align the bias magnetic field to the 111 axis of the NV center, and that's really the key, because then you will get the maximum population transfer and control of the system. So you can now work with, choose whichever one you want. You can work with 0 + 1 or 0 - 1 transitions. So what you do is you start at any point, take a microwave frequency, random 2.87, you can start with that. So typically we can take around 2.87, some number, some bandwidth. right? And you start sweeping your microwave frequency. Now, as an experimentalist, sweeping microwave frequency means that you take a function generator, at around 2.87 gigahertz, you start sending in that, coupling in that signal through a microwave antenna to this diamond, right? And you start pumping, and you see that you simultaneously, when you collect the fluorescence, what you see is when you sweep through the resonance, essentially, what you see is a dip in the fluorescence. And this is how you do optically detected magnetic resonance. And whenever this BZ shifts, this will also shift. And as you see with this red dashed curve, it will always move. And this is, like we discussed here, this is a calibrated system. It's a 2.8 megahertz per Gauss. You know very well exactly what the magnetic field is. This is like a 0th order magnetic field sensor, right? So if you have some magnetic field, you can exactly know where it is. Or in the inverse way, one can also think of it like a microwave detector. So if you wanted to detect microwave fields and you know exactly the calibration in the B field, you can also use it in a inverted way to detect microwave. So people have been doing that as well now to detect as a very wide band microwave detector. So that's also possible. Now let's see one side fact that I would like to mention here, that there is something called a G slack and an L slack, where when you start applying very large magnetic fields, typically we work with about 5 or 10 Gauss, or maybe hundreds of Gauss. Anybody has an idea of what Earth's magnetic field is? Students, yes. Micro Tesla, right? So very, or Gauss means 0.5 Gauss, right? So very small number, right? So we also work slightly above the Earth's magnetic field, but if you work with slightly higher magnetic field, what you see is the PL actually changes, or the fluorescence is actually, somehow it gets incorporated into it. And this paper, actually, I forgot to cite Ashok's paper. You can take a look at this very nice paper where we've done a lot of experiments where we show that how the PL changes with magnetic field, because the contrast also gets affected. And what is interesting is that around the polarization point, or the 520 Gauss, it actually really becomes very sensitive to the magnetic field. And so magnetic field alignment is one of the very critical parts of our experiments. I just wanted to highlight that here. You can go into depth with this paper or read about the details of this. The other aspect of using in our experiment is how do you do control on the spins, right? So our first thing would be to apply a microwave through an antenna, pump the spins, and see, what the response is. So that's the first task. But then if you have a qubit or a 2-level system, you also want to drive the 2-level system and understand the parameters. Before you want to do all sorts of protocols, you want to first calibrate your system. So the way we calibrate the system is just your Bloch sphere. Imagine you start applying a time-dependent microwave field. And this is exactly what is done in every system. Okay, so all the interesting talks that you've heard, whether it's RF, microwave, or in other kind of fields, you essentially apply the same kind of concept, where you apply a time-dependent field, and what you're doing is essentially rotating your spins on the Bloch sphere, and what you see are the very nice-looking Rabi oscillations. Right now, this is the typical standard way to do it. And how do you know whether a pulse is a pi pulse, right? It means that you flip from 0 to 1. So that means you should see the maximum contrast. And so at the point of your first minima is your first pi, right? So that's the typical way in which you calibrate your pi pulse. Now, if you wanted to, now let's say you want to rotate anywhere else on the Bloch sphere, so you can see your pi by 2 pulse. How do you define your pi by 2 pulse? You basically have to now do various levels of experiment. We want to very precisely understand where the midpoint is, so that you can really calibrate your pi by 2 pulse. So you want to do like not just one rotation, but you want to do, because remember, with the more number of rotations, so in theory, it's all delta functions, and pi pulses are very precise in length, right? When you start doing your experiment, you immediately see the pulses have tails because you can't pulse them very nicely, right? So they always come with tails. And so those tails actually add to errors in your sequences. And how would you know whether they have added errors or not? You keep doing this, multiple rotations, and you will see that your Rabi oscillations will not look any more nice and precise like this. They will always get added with some phase will get added on top of it. So you have to keep calibrating until you know with a very high confidence what your pi pulse is and what your pi over 2 pulses are. So all these things really add up to a lot of calibration that is necessary before you can do all the fancy experiments that are lined up, right, for all your quantum sensing. So this is very important. This is the first step where you have to do a very precise calibration of your pi pulse, right, and your pi over 2 pulses. Okay, first step gone. Let's look at the NV Hamiltonian again. Now you see the simple picture of the electron spin is no more true now anymore, because you also have nitrogen, which has a nuclear spin in it, right? And nitrogen can be a nuclear spin of N14 or N15, and similarly you can have carbon 13s around you, so you will have a lot of beautiful things going on although what is beautiful is up to you to take, because one can be a perturbation. On the other hand, it can also be a resource, as we have already seen. It can be a memory, whereas it can also be a perturbation. Now, which aspect you want to harness is up to you. So here I'm showing you the level structure splitting. When you have your, this is your electronic structure, then this is your Zeeman split. Then you have the hyperfine structure. So you can see the very nice hyperfine levels when you have nuclear spin, and this is I1, so I equals to 1. So you can have, and if you have N14 or rather N15, you have a spin half system, nuclear spin half system. And so you see the hyperfine is only split by 2 peaks. So it's 3.05 megahertz. This is 2.16 megahertz. Now, NVs happen to couple to many things. Okay. So on one hand, again, I said, like, it's a double-edged sword almost. You may want to use it, you may not want to use it. Depends on what you want to do with it. So you have a lot of the magnetic field coupling very nicely, beautifully sitting there. You also have D, which is essentially an indicator of the electric term or electric or strain. And then you also have temperature. Now, zero field splitting essentially is dependent on the temperature because it is dependent on the crystal, right? So interaction between your 2 spins, first of all. So therefore, this is a temperature sensor as well. And at least 2 of them you can detect simultaneously in our system. Another aspect of the NV sensors is it's a vector sensor. And why is it a vector sensor? You follow the red dots here. They are the 4 different arms of your tetrahedral, right? And so what essentially you have is there are 4 possible combinations of NV centers that can be formed in a diamond lattice. And that allows us to actually, if you have typically you will have 1/4 each, or it's assumed that you have 1/4 distribution, probability is 1/4. So you get 4 different classes of NV centers in a dense sample. And what you see is, instead of, if you have an arbitrary direction of magnetic field, you can see all 4 in one side along the zero field splitting, and then another 4 on the other side on the zero field splitting. Okay, so now one can start aligning magnetic fields, and one can try to get to cleaner. So you can align along one direction, and so you get 2 peaks, and then you can try, this is zero field, of course you will see only 2 of them, and you see a split here. Ideally there should not be. Typically there is some strain in the structure, and that causes this zero field split as well. And this is, but when you work with large magnetic fields, that in that regime all you care about is the magnetic field, so you don't want to see any of that strain. However, strain is very critical, because when you start doing imaging, strain becomes a very important parameter that one has to take care of. Okay, so in a nutshell, you have NV centers, which are possible sensors for electric magnetic strain as well as temperature. And if you're interested, this is a very nice review article. You can take a look at this review article for wide field, or rather ensemble kind of aspects. Okay, so that I would now, all the theory that you've learned, thanks to Sai, thanks to Anil, thanks to Saikat, and let's try and see how we connect it to our experiments. The first thing is a very simple Ramsey scheme that you already saw in the context of optical clocks. How do you apply the same thing in our context? You can choose your favorite two levels, 0 and -1 or 0 plus 1, whichever one you want to work with, whichever one you have your amplifier for. So that's the more important. To experimental conditions determine which levels we want to work with. So suppose I apply a pi/2 pulse, I create a superposition, and then I let the spins evolve over the equator. You pick up a phase which is proportional to your gamma, your B, and your tau, or your measurement time, right? Now, that's essentially your simple Ramsey measurement. And now you have your short noise limited sensitivity. And I'll talk more about the sensitivity. Let's keep that aside. We've already seen this several times now. So if you have n such qubits, you can do a simple, your classical averaging goes as square root of n. But if you have many number of repetitions of a single, NV center, and you can do many more measurements, that is also possible. So, but it's also dependent on how well or what is your coherence time. That's essentially the main key factor here, that the better your coherence or your coherence time is, then the better your fidelity is going to be. And so you can really get very good sensitivity when it comes to calculating your B field, right? But NV centers are not just classical sensors, right? They are quantum sensors. So we can actually go to the regime where you can prepare entangled states. Hopefully someday somebody will prepare entangled states for an ensemble. It's not yet done, but there are other ways, and Professor Arup already spoke to you about how you can harness the nuclear spin as a resource, as an ancilla, where you can make better sensors, right? Instead of just using electron spin. I will here also show you another example where nuclear spins become very useful, and in combination with electronic spins. So this is a regime that one can really push forward for, or push to get really the harness the properties of this quantum sensor that we have. And hopefully with long interaction times and with better coherence times, you can actually make a very good quantum limited sensor, right? However, these are all very challenging, and I will describe some of the details of this of the different challenges that we face. Entangled states, of course, is a very different regime altogether. Okay, sensing using quantum systems is quite challenging. So I'm going to talk to you about some of the challenges, right? So let's start with a protocol. What is the first step? We prepare, we then transform over to the, the Bloch sphere in the equator, let it evolve, and then do a projective measurement, because remember, these are spins, two-level system. You have this probability of detecting 0 and 1. And so you do a projective measurement, and this is your main limit. This is your fundamental limit of your measurement. You can go to the spin projection limit, and then you can find out what your probability is, your estimation, your B field. Like I showed, this is the nice shining orange that you can see by eye almost if you use an ensemble. So now the rest of the talk is going to be mostly on ensemble sensors. We're not going to talk about the single NV centers at all, because we're going to focus on sensing. And sensing, as you saw, scales with the number of square root of 1 over square root of n, right, with the number of the sensors. Okay, what's the first protocol? Simplest protocol, optically detected magnetic resonance. Let's see how that works. You already can measure all the optically detected magnetic resonance. I've already shown you how to do that. So you can then resolve very nicely the hyperfine structure. So you have a lot of information here, right? If there is any change in the magnetic field, each of these lines will all move, and you have a full Hamiltonian at hand. You can literally fit it back and extract all the parameters, and it's a lot of information that you have. In fact, you have too much information, and all you need is three components of a vector, right? So it's very easy to sort of fit it back and extract from the lab frame exactly all the parameters. However, important thing to note is, where do you want to do this measurement? You don't want to sweep the entire thing. If you are interested to do static, which means that you have enough time at hand and the magnetic field around you is not changing, right? Or changing fast enough, you have, if your measurement can allow, you can do the entire 8-axis or rather 8-peak measurement, and that will take about an hour or so, right? So to get with high enough fidelity. But typically we don't want to do that. You want to do as fewer number of measurements as possible. So either we sit at the, at the minima, or we sit at the slope. And as we have already learned by now, you are all experts that, you should be sitting at the slope, right, to get the highest possible sensitivity, right? So because the slope gives you the maximum amount of change for a small amount of shift in your x-axis, right? So the PL will change maximally here, not here. And this, as you have already learned in the context of your parameter estimation, you can exactly, calculate all these, regimes. However, by eye itself, without knowing any of it, you can still identify what is the best place to sit at, right? Because that is the maximum place where you will be able to get the best contrast, right? Now let's go to the Ramsey experiment. You can also do the Ramsey experiment. So you can do an X and a Y pulse to get it back. And this is how a typical Ramsey experiment will look like. You will have, your signal is proportional to the cosine square. And therefore you will see some sort of oscillations. And here you see very lot of beating. This is not a pure cosine, because remember, there are hyperfines that we are working with, right? So there are 3 levels that are mixing, and 3 qubits are actually, beating with each other. And so you see that signature here as well. Ideally, you should have seen signal like this is a pure cosine, right? But in experiments, if you have hyperfine interaction, you will see something like this, which is with a beating. And you also see the typical decay, which essentially tells you what is the coherence time of your system, right? Now, this is the typical protocol. Flip to the equator, create your superposition, let it evolve, pick up the phases, and that phase is dependent on the inhomogeneities that it sees, and then you flip it back with your Y pulse, and then you essentially create a projective measurement, and you perform the projective measurement. Okay, now let's go to the meat of this entire measurement scheme. How do I know whether I'm going to do a good measurement or a bad measurement, or which one do I choose? A CWODMR looks like this. You have a green pulse that is continuously on. You have a microwave that is continuously on. Of course, for every frequency point, you have to change your microwave frequency, but for a time scale, you keep everything on. And then you read out, of course, with another green pulse, and that also can be on. And this pulse can also be simultaneously used for your readout. And what you see is a peak like this. And here, essentially the sensitivity is actually short noise limited sensitivity goes like this. Let's start with this. In fact, let's start with Ramsey. You have your pi/2 readout, and this is how your signal will look like with a decay time of T2 star. So what does this eta tells us, or sensitivity? This is the quantum projection, right? Your spin projection limited. Now, everything beyond this is actually what makes it worse, right? So here, this is dependent on the fidelity or the time. Tau is the time for which you can do your measurement. N is the number of emitters, or the NDs. Delta MS is just your spin half for system. So you have, or if you're using 0 and -1, so it's delta MS, so it's 1 right now. And then G and mu bu you already know, right? So this is your spin projection limit. This is your golden limit that you would like to hit. But everything else is making it worse. And what are the things that's making it worse? You have a finite coherence time. It's not an infinite system. You have a lot of inhomogeneity in the system. And that decays with this e to the power minus tau T2 star. And there's a factor P here. Now, this P factor is a kind of a fudge factor. I mean, if you try to understand all the decay mechanisms, you will see how this, for every kind of different decay processes, sometimes it will change depending on the spin bath, etc. And there is P actually tells you some more information about the kind of decay processes that are happening. Okay, so you have spin dephasing, that's your T2 star, can be because of inhomogeneities in the magnetic field. So if you have a biased magnetic field that is not uniform over the entire ensemble that you are using, essentially each of the spins will see a different magnetic field, right? And so if you look at this sort of a picture, you essentially, it basically means that you're going to broaden out your line width. right? So there's going to be, a lot of inhomogeneities, and you're going to broaden out. So bias, field inhomogeneities, your antenna. The antennas that we use are never perfect, right? And that also has some sort of a distribution of driving that you can apply, or microwave that you can apply. Every spin is perhaps not feeling a exact same amount of microwave power, and so that also will cause inhomogeneities. And what you see is a loss of contrast here because of the spins not being able to be driven perfectly for each of these systems, right? And so that also causes inhomogeneities. Laser power. When we focus the beam down, you remember this is an hourglass shape kind of a structure, right? So it has a Rayleigh length over which it is nice and uniform. But typically when you focus down, there's always a fixed Rayleigh length. And then depending on the Rayleigh length or the number of emitters, there is a distribution. So there is also inhomogeneity sitting there. So all of these factors actually contribute to your inhomogeneities and essentially contribute to your dephasing time. Okay. Then let's see what happens. What about the red fluorescence that we collect? Are we efficiently collecting the red fluorescence? That's what tells, that's exactly what this contrast number, C is essentially your contrast. So if you collect the photons, so let's say you collect B number of photons for the high state and A number of photons for your low state. So it's essentially B minus A by B plus A plus B that gives you your C, right? And N is the number, average number, so A plus B by 2. That's the number of photons that you can read out, right? And so essentially this parameter here gives you the 1 over sigma R, or essentially it's your fidelity, right? Fidelity of your readout, how well can you read? And this is a very limiting parameter when it comes to NV centers, okay? Because we can't really collect the red light very well. First and foremost, the NV centers are from diamond. Diamond is a very high refractive index material. And what does it do? If you have a high refractive index material, the light actually gets trapped inside the diamond. So you have to be able to extract, it's a, from going from a high refractive index to a low refractive index air, there is a significant jump in refractive index. So ideally that collection is very important. So the better you can make your collection efficiency, the better your sensitivity is going to be. So it's very important to collect very high number of photons, and these parameters ultimately define your photon short noise limit, right? And then you have an overhead time. What is your readout time, right? It's not just your coherence time that matters. You also have your green pulse and your green readout pulse that is adding to your time scale. Right? And so overall, there is an overhead budget as well in terms of your readout time. Now, if you take all of this into account, massage all this equation, this is a more simplified version. If you have a Lorentzian line shape, etc., you get this parameter here. But this is your delta nu is the line width here. C is your photon count, and this is your detector count rate, right? So you can see this is the photon short noise limited, sensitivity that you can get. Again, here you can massage this equation of what is pulsed ODMR. Pulsed is nothing but if you apply a microwave for a duration like almost like a pi pulse. So you're essentially exciting the entire spin. And what you get here, it's almost like a Fourier transform of a CW version. So you essentially get like a slightly narrower, pi ODMR, because you're not exciting the green light all the while, and the green light is limited to a little bit. So you don't see that much of inhomogeneity. So typically a pulsed ODMR will give you a sharper line width than your CW ODMR. So that already brings out the contrasting situations where ideally this is the worst possible mechanism that I would like to use for a sensing purpose. But this is also the easiest because you don't have to do any kind of pulse sequences, right? You don't have to use microwave switches. You don't have to use, all the complicated machinery that you need for performing, your laser operations. You don't need AOMs, etc. So this is a very simple, easy mechanism, but it won't be the best. So pulsed would be ideally the best. But pulsed also allows you to go to the Ramsey, or if you want to use higher order kind of sequences, you can really use this sort of a scheme where you can then split it up into not just Ramsey, but Han, Echo, and so on and so forth. So these are all the different kind of mechanisms. And so finally, if you have a short noise limited sensitivity, you basically massage your readout parameter because your fidelity is much, much less than 1. Your C is much, much less than 1. And so essentially you can get this, where this is essentially the number of emitters times the number of photons that you collect. Okay. What are the most important challenges that we have? As we have already seen, it is the readout fidelity. So how many you collect, how much of red light you collect, that's very important. How well you collect is very important. Number of spins, of course, number of spins, because ultimately it is the number of spins that define, you know, how well, how better your sensitivity is going to be. But there is a catch. If you have too many emitters, then you have interaction coming in. And you can also have that many number of nitrogens not converted to an NV, and those can be just perturbations that are just sitting around, right? So that is I'll just show you in the next plot that you will have a sort of a sweet spot where the number of spins become important. So that's just in terms of the number of spins. But as you already have seen, you need a 532 laser to excite those emitters and to drive them effectively from ground to the excited state. To drive a very high density sample, you also need that much amount of optical power that will create a lot of heating and a lot of, you know, thermal jitter, and lots of other budgets have to be then accounted for. And so there is a kind of optimal location between all of them in terms of number of spins. You also have dephasing time, which is now dependent on all these parameters. And then of course you have your overhead time. The more you have number of emitters, your overhead time also increases because you have to polarize them for that many number of, you know, for that much longer. So that is also important. So these are all kind of interlinked with each other, and there's no real one solution, you know, to all problems. Okay, many spin magnetometer, and this is the kind of plot I was talking about. If you have nitrogen concentration, typically nobody talks about NV concentration, you have nitrogen concentration. So if you really implant with a lot of high density of nitrogen, you see that the T2 star really goes like this. So it keeps falling with higher and higher densities. And the T2, which is essentially your Han echo or your CPMG limited, basically you can see that the sweet spot is somewhere around, you know, 1 ppm or slightly about thereabout, where beyond that it starts to fall. And this you know, really indicates that you don't want too many emitters, but you want just enough to be able to meet your sensitivity numbers. So of course these are all, you know, things that you know by now. Let's see, and let's wrap up this part where you are essentially, we are talking about AC sensing. AC sensing essentially means that you extend with a pi pulse and with CPMG, and these are all the different kind of filter functions that you can define, and you can form CPNG-N, which basically is like a kind of a lock-in kind of measurement. Okay, finally you can get to much better sensitivities, but it's again finally limited by your T1. Okay. Now you can have different kind of regimes, and DC, for DC you would like to do a Ramsey experiment. If you want to do AC, then you can use one of these kind of different pulse sequences. To show in the experiment in the lab, you can see this is the typical ODMR we see in our lab. You can see if we have an N15 sample, so very nicely we can see the hyperfine. I'm just showing you experimental data so that you believe me that they are not just, you know, theory. So you can actually get very nice Rabi oscillations in a high enough dense sample. This is about 1 ppm we have, and it's a layer sample, so you can see a very nice contrast here and distinguish the hyperfine levels. You can then perform your typical Ramsey experiment. You can also perform the Han echo experiment, and you see nice modulations here, and that's because you have an electron nuclear spin interaction, and that gives you this kind of a modulation that you see. Okay, a quick look at how experiments really look instead of just looking at pictures. This is the confocal microscope, completely home built. This is the wide field microscope that I'll tell you about more. This is where we do all our ensemble experiments as well. Of course, along with all of this, you also have a lot of electronics that is necessary for controlling all these spins. Okay, take a break. I like this picture, and thanks to Carl for pointing out very nice pictures. I pulled up some of my pictures. This is actually my husband in sequoia, giant sequoia, with a giant sequoia tree, and this is how I see science as well, right? You build something and then you start building around it, and it's actually, there's many things to look up to. So that's how I feel about science as well, and technology development as well. Okay, moving on. Let's look at an application. Okay, rotation sensors. Rotation sensors are very important. We've not talked about rotation sensors so much in this conference yet, but I think Sai briefly mentioned about gravimeters, but not in the context of rotation sensing. Gyroscopes. All our phones have gyroscopes. You can detect things rotating. Your phone flips screen because you can sense rotation, right? When you change, so essentially you have a gyroscope sitting in it, and it's a MEMS gyroscope. It's a small chip that's sitting in your phone, and you have various different kinds of gyroscopes that are built for various different technologies and for various different applications. So no one gyroscope fits everything, right? And it's the same for magnetic field sensors. No one magnetic field technology will fit in all regimes. So you have to see what kind of application you want to develop it for. So we can see that you can make the best kind of gyroscopes. Also now with atoms, you can make, so you can really push towards basically sensing rotation. Okay, so if you want to use a spin for sensing rotation, what is the main mechanism? Essentially, when you do your Ramsey, if you have your lab frame rotate, then you have your pulses also have to be rotated. And so it's like you're sensing the rotation, or in a very simple, very zeroth order concept is if you have, your standard north-south directors, right? You can, if you rotate that, right, you will see basically your needle will also change, right? So there also your compass needles, right? So if your needle will also rotate, and so from that rotation, you can make out how much you actually rotated your compass needle. So that's essentially the main principle which is used for detecting spin gyroscopes for rotation sensing, and that's exactly what we can do. And this is what we were starting to think of when we were working with NV centers with ensembles and trying to see if we can sense inertial rotation. And of course, here the important thing is, and I'm going to go a little bit fast here, because the important thing is that while electronic spins are sort of good enough sensors, nuclear spins are actually better rotation sensors because it doesn't depend upon your gamma. The rotation does not depend on gamma. So while electronic spins are very good magnetic field sensors, and nuclear spins are worse because your gamma is 9,000 times smaller, nuclear spins are better in terms of rotation sensing because rotation doesn't have gamma. Okay, and so therefore using this sort of a simple concept, we wanted to see if there's a possibility of demonstrating solid state based rotation sensor all on a chip. And this work was actually proposed by Ashok and Paula in 2012, and then when I joined MIT, we tried to actually see whether we could build one of them. And we started off with building one of these sort of a small chip scale, diamond with a photodetector, collecting all the light with, a filter, and trying to see if we could get, excite the nuclear spins. Now, nuclear spins, when you start working with nuclear spins, it's a little bit hard because you have to now couple in RF along with microwave, because the nuclear spins are in the RF regime. And so therefore what we have to do is first figure out how to polarize the nuclear spin. Remember, the first step in any sensing experiment is to start with a very well-known state, right? And so you have to first know how to polarize the nuclear spin to a very precise state. And once you do that, you can essentially drive the nuclear spin between these two states and then use the electronic spins to read out the nuclear spin state in the NVs. And NVs actually allow that. More detailed references, this you can find that this was actually done way back in 2009, and you can see that you can apply a microwave pulse to first get it, prepare the state, then you apply a mapping pulse to finally read out the nuclear spin state. And in the nuclear spin state, you will see exactly how the nuclear spin is behaving, that is coupled to the electronic spin. Now, how do you polarize the nuclear spins in an NV system? You have to work very well for aligning. Now, this is the easiest scheme. Of course, you can apply many pulse sequences. There are several pulse kind of protocols as well. But the easiest way is to actually apply a bias magnetic field at around 500, 520 Gauss. Okay. But that alignment, like I showed you in the figure before, it's an hourglass figure, right? So the PL contrast will significantly drop if you don't align your field very well. Right, so that means that you have to precisely align with your 1-on-1 axis of the NV center, and that requires some sort of a geometry like this, where you can apply the field. And once you do that, and this is data from MIT, when we first did full nice polarization, you can see you start off with a 3 hyperfine split line, and then once you polarize, you can see that the nuclear spin essentially completely polarizes, and that's because of this interaction in the excited state. The spins actually get transferred very nicely to this down level. Okay, all good. We have polarized our nuclear spin. Now it's time to perform some experiments on them. So now you can perform your standard Ramsey experiment by just applying the correct, frequency and the correct pulse length. You can perform your Ramsey experiment, and you can see here the contrasting T2 star times between for the electronic state versus your nuclear spin. You see this is nanoseconds, so 403 about 450 nanoseconds. Now it has become a little bit better. You can push it, as I already showed you in the plot, right? Now nuclear spins can really easily go up to several, almost milliseconds of time scale when it comes to the coherence time, and that's primarily because the nuclear spins don't interact so much with the environment. And so you see that in your coherence time. And here you can see your control of your nuclear spins. And this is the kind of schematic of the setup that we used. And so finally, I just want to show, this was in 2012 when Ashok proposed the method. In 2019, we published this paper where we actually emulated a rotation sensor. We didn't really do a full rotation of the system, but we applied kind of a stupid thing where you just control the phase and pretend that you're doing a rotation measurement. So we did some sort of that. And then in 2021, actually, this is Alexei Akimov's group from Russia. They actually published the first work where they use exactly the same geometry, but they finally were able to rotate the system, and then they are able to see very nice rotation sensing with the NV centers themselves. Now I'll tell you a little bit about our work. Where we realized that we were not getting the best kind of rotation sensitivity per se, but we wanted to push to, looking at understanding the stability of the sensor, because remember, the rotation sensor not just has to be sensitive, but also stable. Ideally, if you want to use it in a situation where suppose you want to use it in a rocket or some phone which is falling, for instance, it has to be able to maintain that thrust, right? Or be able to take that stability or see how well it is stable over days, right? And first time we started looking at what we call a sensing feedback mechanism. And in this case, what we started doing was that, all of this is sort of your quantum sensor. This is my electronic spin. It is seeing a lot of noise in the system. It's decoherence limited sensitivity. But what if we could feedback somehow and correct for some of the decoherences? And for that, we use the nuclear spin as our main rotation sensor, but we use the electronic spin as a resource to measure the environment, because it is really a better sensor when it comes to measuring the environment. Right? So we started looking into some basic feedback mechanisms, and in fact, this work was one of the first works related to a simple cross-sensor feedback, where you could just stabilize the frequency of the pulses. Remember, if the frequency of the pulses change, then you're not going to be able to drive your spins as well or read out your spins as well. And so any pulse error can be maybe a simple way is just to correct for the first thing to correct for is the frequency. Right? And so we started doing that, and we basically used as a computer along with an electronic spin as a sort of a communication channel between spin sensors. We started to measure the environment with the electronic spin and then correct the frequency on the nuclear spin. Okay, and that's how we improved the stability of the system. Okay, and of course you've heard a lot about Allen deviations. I'm going to go back to Allen deviation because that is what tells us what the stability of the system is. And here you can see Allen deviation basically, sort of tells you what are the different kind of noise that your system or the sensor sees. If you have correlated noise, if you have sinusoidal noise, if you have random walk, if you have bias instability, these are all the things that come up in an Allen deviation. And so it's one of the very key important concepts that one has to sort of master when you want to look at stability of systems. So we also did the same thing. We started trying to understand the stability of our sensor if you have an electronic spin versus if you have of a nuclear spin. And you can see very nicely, right? Allen deviation shows that the electronic spin starts becoming unstable, after some point of time, maybe a few hundreds of seconds. And then this measurement was actually taken over 12 hours. And it takes 12 hours to generate this kind of a plot. You can see that there is something that starts to show up here. In fact, we did the measurement for more than 12 hours, and that's why this actually starts to show up. We started questioning what was happening, and we realized later that our AC had a turnover time exactly somewhere in 12 hours. And this is a periodic oscillation. So when we did repeated measurements over several, there's an AC time scale that actually pops up. And to see whether it was really happening or not, we started measuring the temperature in our lab. And you can see here that there is a global, change in temperature, but there is also a periodic, daily change in temperature in the lab. And the sensor, was actually picking the daily fluctuations in the temperature, and you can see very nicely those oscillations were there. So we first did not understand how to do this, and this is my almost postdoc very naive days of understanding how to interpret Allen deviations. We started looking at what are the ways in which these correlated noise pick up or sinusoidal noise come up. Then we started investigating with hair dryer. We did laser power modulation and lots of mechanisms just to see what was happening to our sensor. Is it actually susceptible to all these kind of things? And then when we modulated all of this, you see very nicely, if you don't have modulation, something happens. If you have modulation, it really picks up very nicely in the Allen deviation. So when we were confident about all of this, we were like, okay, our sensor is actually picking up all these information. So now let's try to correct it. Well, if you then try to do frequency correction of your pulse by just intermittently doing a frequency correction, you can see you can almost correct for it. You apply a periodic noise. When you start looking at the optical signature, you can see very nicely that the modulation is more or less corrected for. But there's some effects of not being able to correct as well in some time scales. And that's because our pulses are not perfect, and we are not able to perfectly correct for all of this. Now we started to really work more of this, and we could see that you could correct in some regimes, but you could not correct in many of the regimes. And then we started to see whether there was a way in which, at that time, we started calling it history-based measurement. Okay, so we already knew that the temperature was changing in the lab, or some magnetic field was changing in the lab. So we could take some history-based measurement and predict what the next point is going to be. And now all of this has gone into the class of Bayesian and machine learning and all sorts of things. But at that time, we were not worried too much about all of these big buzzwords, but we were doing a very simple measurement where instead of doing a full ODMR measurement, we're doing a 4-point measurement. So essentially imagine an imaginary Lorentzian here, but we took 4 points here. So 2, 1, 2, 1, and then we fitted and found out what the frequency is, pulse frequency, and then we changed it, and over time we started predicting what so over time you can start predicting what the frequency change is going to be. We fed it back and we started to stabilize the system, and very nicely you can see that you can feedback over feedback, and there are many regimes that one can work with. Right? So you can see that in the Allen deviation plot, and this was the first work on really using electron nuclear spin cross sensor feedback system, which we worked in, was then finally published in 2019. That was most of my postdoctoral work essentially. Okay, so we now switch gears. In the last maybe 20 minutes or so, I want to tell you about magnetic field sensing. That has always been my interest, and from rotation sensing moving towards applications of magnetic field sensors and trying to see how we can use a dirty system like NV centers, and hopefully we can really shrink down everything, make a small little device, and just like Tanya already mentioned, you make a small clock, we want to make a small portable NV center system. And that's already, and Professor Arup already showed you that little tiny sensor. We are also working somewhat in those directions, but here I'll be telling you about the imager that we have built. Advantage is, remember, we use a plate of NV centers, and so that gives us the opportunity to use it as an imager for magnetic field. Now we also look into the other quantum regime where you have not just quantum for biology, but also quantum biology. And so that's something that it's there in the back of my mind, but not really. But you can, there's a lot of developments that are going on now. So this is also becoming interesting. But magnetic field sensing has always been of lot of interest in this community. You already saw that if you use a single spin, you can look at the dipolar coupling between a spin and a protein molecule and try to reconstruct back the entire, sort of the structure of a protein molecule. You can then also have the kind of scanning tip magnetometer, and you can look at different materials. And of course, this is a whole range of, there's actually the best kind of sensors are squid sensors or atomic vapor sensors, but NVs fall in a nice regime where you can also use them for imaging, and that's what I feel really is powerful about the NV system. Okay, so how does one do imaging? You have a slab of NVs, you have a layer of NVs, and then you put a certain sample that you would like to investigate, and you excite with green light, collect it. Instead of using now an APD or a detector, you basically put it on a CCD or a CMOS camera and start imaging all of this. Now there are several numbers here. These are now becoming better and better every day. People are pushing the limits. In fact, I need to update this part because now I think the best DC sensitivity is about 500 femtotesla or even lower now. And AC is almost about this. And spatial resolution is of course 250 nanometers because it's diffraction limited. In a wide field setup, it's more like 1 micron instead of 250 nanometers. And that's because it's actually coupled to the sensitivity. Whereas the field of view can be very large. So that is one of the key advantages of an NV center, that you can have a very large field of view, but you can also have a fairly very high spatial resolution to get interesting images of various types of samples. And one of the applications that I have always been interested in is kind of looking at biology and for neuron and neuronal imaging. However, I'd like to point out some of my favorite applications of imagers, and I feel these are really the kind of landmark images that people have taken. This is from JP's group in Australia. You can see here vortices in a superconductor that have been imaged with very, very low optical power, in fact. And you can see the nice dynamics of the, the vortices. This was one of the first ones in Basel. This was taken for, again, a superconductor where they actually studied some phase transitions that were happening. And now there are several groups who are looking into these kind of applications of various 2D ferromagnets, various different kind of condensed matter systems, where you actually want to look at a map of the magnetic field, look at not just the map of magnetic field, but what is interesting in this kind of a measurement is actually a J. So from the B, you can reconstruct the current. If there is a flowing current, you can reconstruct the current density, because this is a vector information that you already have. And that is really powerful because now you can look at something like hydrodynamic flow of currents. Now in graphene, this was studied in graphene, and now there are different kind of other sort of 2D materials that are being exploited and studied. And you can see here, there are many different kind of things that are happening, and you can actually study them in real time. Now, of course, these don't tell you anything about real time. These were all static. I'll talk about real time. So here, this is another extreme where the diamond sensor is used with, and this is the kind of example that already you've heard about. This is a C. elegans worm. It has a single neuron. When you start, hitting it with some pulses, it starts emitting a neuronal pulse or a signal, and it was measured with an NV center. And you can see this is of the order of, say, few hundred picoteslas or so. And in fact, if you want to now start measuring a cluster of neurons, and that's what we are aiming for, then you have to actually think about how to reconstruct vector magnetic fields in 3D and also do dynamic measurement. And that's where our research comes in, where we've started building, imagers which are more like this, where instead of just mapping a layer, we want to map 3D images. Right, and that's and here we use a spherical cow approach of a neuron, where we build micro coil structure which are fabricated in gold over silicon dioxide, and we make micro coils, and I'll show you some images of how these micro coils look like. Okay, so before now, of course, when you do things in wide field, you can't really do pulses very well. Okay, because remember, wide field means there are 3 challenges that I already addressed before: laser inhomogeneity, magnetic field inhomogeneity, microwave inhomogeneity, right? So when you excite the spins, you don't excite them uniformly. So if you want a plane of imager, it's not very uniform. So if you have pulse driving, then that's not the easiest thing to do. However, we are doing it still. Another technique that is often used by atomic clock people, all standard spectroscopists, is to use a frequency modulated version of the optically detected magnetic resonance. In this case, instead of just using a single frequency, you do a frequency shift keying method, where you keep modulating that frequency, and what happens is that the PL starts getting modulated. Right? And so instead of seeing a Lorentzian, what you see is a you can see this sort of a profile where it's a differentiated signal, right? And for extremely novice people, I think a very simple version of understanding what is happening here is that this is called a lock-in detection, where you basically multiply with your main signal with a modulated signal or a local oscillator. And then you take one of the quadratures. So you low pass filter it, and you basically, what you do is, instead of measuring the entire noise from a very wide spectral range, you only limit yourself to your modulation frequency, which is very well known, or from the local oscillator. Right now, this is the standard lock-in detection. And why do you get, instead of a Lorentzian, why do you get a differential? That's because if you have your sinusoidally varying, let's say sinusoidally varying signal, the voltage that you detect with your photodetector goes like this. And then if you just assume or make sure that your A parameter here is kind of small, you do a simple Taylor expansion, you can see that the voltage out is proportional to the derivative of your signal. So this is a very crude way of understanding what happens to a lock-in detection. And this, instead of doing a standard ODMR, this is a better way, and you can do much better sensitivity. And you can get here, you can see here that if you have field on versus field off, you can get a much sharper slope here that will enhance your sensitivity for measurement. And this is a very simple way, but this is if you had an integrated signal from a photodetector. But remember, we are trying to do imaging. How do you do imaging of lock-in detection over so many pixels, right? Now that's where a handy camera came into action. This is a Helios camera which has a lock-in per pixel lock-in. We started using this, and Ron in Harvard, when he was in Harvard, first started using this sort of a camera, where every pixel is actually a lock-in detector. Okay, and what you see here is the ODMRs for each of the pixels plotted with respect to microwave frequency. And so you can see these are just 3 arbitrarily picked up frequencies here. You can see all the ODMR spectrum in each of these frequencies. So now, if there's a fluctuation in the neighborhood of pixels, you'll actually see these individually move. And of course, we don't have to do a full trace of the entire spectrum. You can look at one point and start measuring about that point as well. Then we started looking at the sensitivity, important parameter to calibrate. You can see that there is definitely a sensitivity distribution. Now you see a hole here, and it turned out that when we were pumping it with a lot of high power, because this is a very high density sample, a dust got stuck there and it actually damaged our objective, and you see that in our map here. So unfortunately, the most sensitive part got damaged because there was highest power there, and of course it got damaged. But we see a median sensitivity of 700 nanotesla per pixel or so. And you can see we varied different parameters, for instance, the modulation frequency and all the modulation depth and microwave frequency, etc. And you can see that there are sweet spots where the noise of the system has to be calibrated. So we worked around all of that. And finally, when we started imaging this sort of a microcoil with a chip with NV centers. And for the first 3 months, we saw nothing. We only saw this. We were very, very extremely agitated in terms of why we were only seeing, images of the microcoil almost imprinted on our fluorescence, but not the magnetic signatures. And we were completely puzzled for 3 months and trying to formulate all sorts of reasons why things were happening, and maybe some new physics was also cropping up, and God knows what all happened. And it turned out there was nothing like that. And it's something very, very silly. It's essentially because we had a layer of NVs. Okay, so, and on the diamond sample, it's very difficult to know which side your layer is. And it was rather unfortunate that we actually mounted our sample in the inverse way. But it also means that if your sensor is very far away from the sample, then you basically see a very blurred map, and you essentially will not see any of the map. That is what it basically means, that if you have a thick sample of 500 microns, you don't see the features of a coil that is a few microns, and which has a field that is less than 101 Gauss or so. Right, we are in fact in very small mind. So when we finally did a confocal image of our sample, we realized that it was obviously on the opposite side, and so we had to revert our, remount our sample, and then it was all good. So important parameter to note here is the distance between the sample and the center is very important, and right now it's limited by the glue, the thickness of the glue. So it's about 10 microns or so. We are trying to push it. People claim that they can do 100 nanometer. We haven't yet been able to less than 4 microns. So let's go back to our mimicked architecture. You can see here, this is the head, this is the tail of our mimic neurons. We looked at this, and so we started doing static. Very nice. You can simulate all the BX, BY, BZ, single axis NV measurement. And then when you finally do a projective, measurement, you can really reconstruct that. Now you start to see the magnetic field image, right? You have your red and the blue, and essentially the coil is actually the white part that you don't see here. Because here the B field, when the current flows in the coil, you actually see the B rotate. And so what you see are the high and the low regions of the B, and that's what you are seeing here. Now, you can reconstruct back your BZ feature here. The hole is of course there. That's not gone anywhere. And then we started to look at temporal feature. And this is the real key part of our invention here, is that you can actually do temporal magnetic field imaging, where if you modulate the current in your coil, you can actually see fluctuations in the magnetic field. And in fact, you can also see harmonics of the magnetic field. This is one of the first kind of magnetic field imagers which has temporal features in it. And then we started looking at our coils, and you can see very nicely, you can resolve the fluctuating magnetic fields that are present. Now, this is just one such example where this kind of temporal imaging can be applied. But now you can extend this to any circuit pretty much. You can try looking at mapping different kind of circuits and different kind of architectures. And now I want to tell you that this is where strain improvement becomes very important, because every anomaly that is there on your crystal structure will then get mapped onto your magnetic field sensitivity. And that's where something called a double quantum architecture becomes very important. If you could somehow do pulses, and this is what Ron's group did, is if you have, instead of using the 0 and the -1 level, they use the plus and the -1 levels. And the +1 and -1 levels are like, doing null measurements. You basically cancel out the features because of the temperature and the strain, because that is what changes your, D. And so once you do that, you can see stark difference. See, this is without doing double quantum. This is with doing double quantum. You can see how uniform your field of view has become. And this is a higher order protocol that one can perform by using this sort of a architecture of doing double quantum. And that's the advantage of doing pulses, that if you could really extend to doing pulses and pulse schemes, you can actually make your the features very prominent. But you can also, then you have to also give up a little bit of your time scale. You cannot do very easily fast magnetic field imaging. So it's a question of what you want to do. So there are also some other schemes that came up. And so I want to show you one sort of a feature that we try to emulate, which is essentially the neuronal kind of signature. And you see here that if it is 394 milliseconds and 427 milliseconds, you see a dead spot here, and that essentially corresponds to the transition between these two signatures. Now, I'm just going to show you a video here. This is if you have microcoils that you have current flowing in them, and you can actually image them. So here the scale bar is about 20 microns. You can really image, currents that are flowing in microcoils, and you can immediately see that this becomes a very powerful technique to do temporal magnetic field imaging. So okay, so with that I'll summarize. So we have NVs. I talked to you about details about NV center and NV center sensitivity, and how you can really enhance the sensitivity, what are the limitations, what are the challenges of the field. And we then used to do some rotation sensing. You can see that we were able to improve the Allen deviation or the stability of our quantum sensor. And then finally, I talked to you a little bit about another application in the realm of imaging of magnetic fields, and how you can do temporal magnetic field imaging. So with that, I have to thank all the people who have done a lot of hard work to set up everything, and all the collaborators and funding agencies, of course. And there is another one that I really like. This is in Bryce Canyon. I really like the hike here. But there's something that I would like for all the youngsters who are sitting here and who want to do hard experiments and hard theory, that most of the time research is all about looking at walls. Okay, and you stare at your screen, or you stare at your experiments, and 99% of the time things will not work. But you have to improvise, and you have to keep improvising, and you have to keep working at it and keep at it. And so when you start improvising, it's no more a wall, and you can really go through the wall and actually try and become more independent. And creative thinking is what gets you to doing creative research. And with all the precision measurements that you're seeing, those are heavy experiments. And then of course there's a lot of heavy end theory. Most of the time you're going to just see a wall, and you have to really walk through that wall by being creative and being persistent, and try to really get through a lot of difficulties. Will only through persistence can you actually make good experiments and precise experiments. Okay, so thank you very much for your attention. I'll be happy to take questions.
Questions?
So ma'am, you have talked about the sweet spot in terms of concentration of the NV centers. So keeping the concentration constant, if we just change the tau, so
change the tau meaning the
yeah,
readout time?
so decoherence time. So with decoherence, the number of spins or the NV centers participating, it is also decreasing. So yeah, decoherence.
No, so it's not like number of spins are participating, or it's just that the overall interaction sort of limits you the amount of time that you can interact with the system. Or it's like saying how good my sensor is in terms of how what is the highest fidelity that you can read out for. That's what your for instance for a Ramsey kind of a measurement will give you. Yeah. But you're always interacting with the same number of spins. It's not like you're interacting with the less, you're not changing the, your beam width or anything. That's not happening.
So how I am thinking, so with decoherence, we are losing some signals we are losing some signals from each spins. So
It's not like losing signal
not
from
like
each
that,
other.
okay.
Yeah, it is not like that. You're always getting signal, but they're all interacting in a way so that you're destructively sort of getting, less signal. Yeah.
okay. And
Yeah.
other question,
Canceling each other. Yeah.
and other thing, so what is the dynamic range of this system? So when we talk about sensitivity, so for if you want to get that level of sensitivity, what is the magnetic field range?
Yeah, that's a very good question. So your magnetic field range will obviously be limited to your sharpest point of your slope, right? So whatever that length is, maybe a megahertz or half a megahertz or so, right? But that is not the only way you can be limited to, dynamic range can be controlled by other mechanisms where you can do more feedback schemes and you can increase the dynamic range. And we are in fact working on something like that recently. Yeah, we've already shown that you can do a small kind of a feedback loop where you can extend and track your ODMR and actually increase the dynamic range. And so you don't have to be limited by that line width. Okay, you can actually keep tracking your ODMR itself and track the bias field, and you still will be able to increase to a fairly large dynamic range. Yeah.
Okay, thank you.
Hello, ma'am. You said that you can use the nuclear spins to for better rotation sensing. So, is there any difference if you use nitrogen 15 or carbon 13?
Yeah. See, nitrogen 15 is already there, right? And the thing is that you also want to be able to read out the spins correctly, right? And the added advantage of using, so there's no really difference, but the advantage of using N15 rather than, in fact, not N14 also. We used N14, but N15 is much better because N14 has a quadrupolar coupling with the electronic spin, whereas N15 does not have a quadrupolar coupling. So it's almost like an independent spin that is sitting, and it's like an atom that is sitting in a solid state matrix that is feeling the rotation. Yeah, but really, but carbon 13 is also difficult to find. It's only 1.1% in an entire, unless you get isotopically pure carbon 13, which is very difficult to get in a sample. But already getting isotopically pure like the sample that we have with N15 is already very challenging. But getting another carbon 13 is even more challenging. Yeah.
And if you have, if the magnetic field that you want to sense is, if it is not aligning properly with the NV axis, then the spectrum changes depending on what the direction is. So does it, so in order to sense better, do you need it to be aligned properly, or it doesn't matter like which?
Absolutely, it matters whether you align it properly or not. But so let me just show you, let me just address it here. You can see the ODMR here, right? This is very non-uniform. Ideally, when you want to do a full vector magnetic field sensing, you don't need 4 lines. You can use 2 of them on 2 sides, and that is enough to reconstruct back the vector signal. So what you typically would like to do is align your magnetic field somewhere between the 2 axes so that you get uniform distribution between 2 of them. So you get, so contrast is, remember sensitivity has a C factor in it, right? So the better your contrast is, better your sensitivity is going to be. So if you have a non-uniform distribution in your ODMR, you're going to get, your sensitivities are going to be slightly different for each of the lines. So while you can do single axis magnetometry, and we've already done that, if you really want to do a full vector and use the power of vector nature, then you should align your magnetic field very carefully and be very precise with the magnetic field, because the more you optimize your contrast, the better your sensitivity is. And also the line width also starts narrowing down if you optimize very well, because basically what's happening is your hyperfines are then aligned very, very precisely, and so you don't see the inhomogeneities kind of popping up. Yeah. Plus your driving will be also better. It's all coupled kind of a thing, but it takes a lot of patience and a lot of, figuring out how to align the magnetic field and get very good precise field. So ideally, the easier way to do is use a Helmholtz coil, and that's much better. Instead of using the standard, we use neodymium magnets or even samarium cobalt. These are standard magnets you can buy off the shelf, but it's better if you use a Helmholtz coil, which has 3-axis control, and then alignment becomes super easy, because then it's just a feedback direction in terms of measuring the, the PL. You can, continuously monitor the PL. In fact, the measurement that I showed you here, this was a code that Ashok had written. This one. Yeah, this was a code that Ashok had actually written, where we monitored the PL of the NV center, and every time we move the magnet. So the magnets, in fact, here were motorized magnets, and the sample was also motorized. So we could monitor the PL, and this was actually an automated plot that was generated, that as you move the magnet, you can see the PL distribution. And what you want to do is best align to that, the center line that you can see. And this was all done through a feedback. You measure, align, and then you can set through the through your contrast, you can set very nicely what your magnetic field is. And in this case, we could do almost at 0.5 degree precision. We could align the magnetic field, and that gave us the best sort of, you can go read there's 2 papers there, one quantum interpolation paper, and the other one, there's another paper which is essentially AC sensing. So it's a lock-in detection paper, where they use exactly the same concept here. So it's very important to align the magnetic field very, very well. Yeah.
Thank you.
Any other questions?
Wonderful talk, Kasturi.
Thank you.
Do you have any kind of shielding that you use for your setup from Earth's field?
No, as I showed the picture, our setup is actually wild open. Actually, it's crazy. There is all sorts of electronics everywhere, and we don't shield anything from anything. We are all happy living together. So, yes.
Does it like affect your measurements?
Ideally, we would like to shield it, but we are also trying to not shield it and use the NV center's properties itself to help us shield it, because we can do a lot of these, common mode error rejection, right? Because we have so many lines there, and if there are laser fluctuations also, you can also do common mode rejection for the laser noise itself. And so for the magnetic field, you can use both the 2 lines on 2 sides for the same, ODMR, and you can do temperature correction as well as field correction. And anyways, the field is corrected because this is over the top of your Earth's magnetic field. Yeah, so you don't really need to take care of any of those. That's really the beautiful, aspect that is sort of came from nowhere in diamonds, sort of. It's actually, interestingly, diamond has been known since NVs have been known since 1960s. The first paper of locating defects in diamonds and different host of defects was in 1960s. There's an old material science paper that you see. And first NV paper, in fact, I saw was in the 1990s from Arup and Fedor Jelesko's group. And then onwards, using the spin came in 2008. So it's been some time, and then people started realizing all the different dimensions in which NVs can be applied to, because it's so unshielded. It's a very dirty system, actually. Yeah.
Any other questions?
Yeah.
Hi, ma'am. So you briefly mentioned that you want to do 3D imaging. Get maps of 3D things. So, but if you're using a confocal microscope, won't it be a problem because you're shifting the Z every time?
We don't use a confocal microscope for
that.
3D imaging. For the we use the wide field microscope actually for the 3D imaging.
Okay, but so that is just like a wide field image you want to get in 3D,
Absolutely.
not a PL or anything.
Yeah. So you have to wait for me to give my next talk
Okay.
at some point, where we are actually doing the 3D imaging, and I'll tell you how to do the 3D imaging. Till then, you just have to wait a little bit.
Yeah. Thanks. Oh, just one more thing. So what will be the applications of that, and like what size in Z are you trying to?
Yeah. Absolutely, very good question. What are the applications? A lot of applications actually. So any kind of chips, 3D layers of currents, you can image with that. So essentially, we are targeting at least a few millimeters of 3D imaging.
Few millimeters. Okay. So with a 100x objective, is it?
Currently, we are using a 100x objective,
Okay.
but we are not using a 100x objective. What I didn't mention here is that we are not using a 100x objective like a standard 100x objective.
Right.
We use it in the wide field way,
Okay.
where you actually use it in the inverted. It's like a lens where you focus in the back focal plane and you
Okay. Okay.
use it as a a collimated beam on the other side.
Right, right.
So it's not a standard. So it's not
Okay,
your beam is not small. You actually
Okay,
try
okay,
to
okay, okay.
expand it as much as possible.
So the working distance doesn't really matter in this case.
Working distance here is about maybe, I don't know, I don't remember the exact working distance. I think we did a very careful collect.
Okay. Okay.
We are very
Yeah.
tight on this, but there are ways around it.
Yeah.
We know how to do it.
Thanks, ma'am.
Yeah, maybe a naive question, but how strong is this optical transition to the effects from arising from the local strain in various crystals?
Local strain, yes, local strain I already showed you, right? So if you have a lot of, let me just pull up again. So if you have a lot of strain, I can't give you the exact number of strain, like what is kilohertz, megahertz. Maybe I'll just pull up that figure. Ron's figure is there. So where is it? Let's see what it is. Here you can see, yeah, it's a delta megahertz. You can see this is about 0.2 megahertz or so, right? So there's a lot of strain that can really get coupled to the system, but you can correct for it also. Yeah.
And also, do you have like problems due to like surface charge traps and like in terms of spectral diffusion or so?
Yeah. We don't see that too much in the wide field because there are too many. We are not working with the sparse samples. Sparse samples are, that's where the charge trapping actually becomes critical. If you're doing like a kind of a biological sensing, so there those charge traps become important. But here this is a very dense sample. So in fact, this is a 1 ppm sample. So that's about say 10 to the power 12 or 10 to the power 10 NVs per centimeter cube. So that's a very high density of NVs in a very small layer. This is a 1 micron layer that we use, about 1 to 2 micron layers of very high density. So you essentially don't see too much of it anyways. Yeah. But if you did something that was like sensitive to charge, like small charge density distributions, that would cause problems in biological sensing, and people take care of that very, very carefully. Especially like, the Booker group or even Peter Mora's group, they do a lot of these, charge kind of calibrations. We are not so much, in that regime at all, where we care about the charge at all, because we are working with fairly high fields, that would say. Maybe when we start hitting the less than 100 picotesla, we'll have to start caring about all these different things that may contribute to effective, decoherence mechanisms.
Thank you.
Any other questions? Okay, good. So even though Kasturi promised another exciting talk, it's not unfortunately going to be in this.
Maybe
in
not
this.
so soon. We will probably.
So let us thank Kasturi once more for a very nice talk, and I have pleasure of handing over the elephant to her.